we'll have Shreya Mehta from Imperial College, who will be talking about non-commutative extensions of diffusions and hypercoercivity. So whenever you're ready, Shreya.
Thank you for the introduction. So I'll be talking about the non-commutative extension of diffusions and hypercoercivity. So first, why do we need this non-commutative extension? So during the early development of quantum mechanics, it was realized that a non-commutative framework is necessary for the understanding of events at a quantum scale. And in the quantum setting, the quantities like position, momentum, or coordinates does not necessarily commute, unlike the classical setting. I'm not able to. Move to the, just a second.
That's fine.
Yeah, I'm not able to move the slide actually.
Try sharing again.
Okay. Oh yeah.
Lovely. Thank you.
Sorry. Okay. So today I'll be first talking about the non-commutative analog of the classical Hormander theory, and then I'll give a non-commutative framework for proving hypercoercivity. So we recall that the Hormander theorem, if we take the operator to be the sum of the squares of some fields and the sum of some linear terms, it is hyperelliptic if these partial differential operators satisfy this Hormander rank condition. That is, the rank of the Lie algebra which is generated by these operators is n. So this is a very useful theorem for in the application of the partial and the stochastic differential equations. So here we saw that these are the classical fields, and we know that field is a quantity which is defined at each point. Now the classical field has some kind of source like particles, which results in this field existing at every point. So the quantities like position and momentum, they are defined as the property of these particles, right? But in quantum mechanics, these quantities like position and momentum, which were just mere numbers in classical fields, they become operators. Then in that case, they not necessarily commute, right? So they can, this means that these quantities cannot be defined precisely simultaneously, like in the classical setting. So the quantum field cannot stay still. It's under this constant state of fluctuation. You know, so it's like this bubbling soup of particles and antiparticles, which we call the creation and annihilation operators. So we define A star to be the annihilation operator, which reduces the number of particles, and A to be the creation operator, which increases the number of particles. And we define the CCRs, which are the canonical commutation relation, where the commutator of AJ and AJ star is some identity, and the other commutators are 0. And we define the derivation operator to be equal to the I commutator of V and W. So these are just linear operators which will satisfy the Leibniz rule. And we can take this as the non-commutative generalization for the partial differential equations. So now we are moving from the spaces which has the fields xj's to delta xj's. And we define these derivations on the algebra, which is generated by these creation and annihilation operators. So for a non-commutative setting, we can define the operator L to be the sum of the square of the derivations and some linear term. And by lifting theorem, which was introduced by Rothschild and Steen, any Hormander type operator, which is the sum of the square of the fields, can be approximated by a sub-Laplacian on a stratified Lie group. So now we want to define some examples of nil-potent Lie algebras, which can be generated by the derivations with respect to the operators which satisfy these CCRs. Which means that we want to find such nil-potent Lie algebras, which can be modeled using the derivations, delta W of some, which is a function of some copies of CCRs, which is going to be a monomial or polynomial, such that the commutator of the derivation with respect to these operators is equal to I, the derivation with respect to the commutator of these operators. So we found some examples, and the easy example can be the Heisenberg-Lie algebra, which is defined by the commutator of two operators as the third one. So these can be generated by the set of derivations which are given here. So the commutator of the first two derivation would give the third one, and the rest of the commutators are 0. Similarly, we have this another example, which is the algebra of dimension 4 and rank 2, which satisfy these two commutator relations. And this can be generated by the set of derivations which are given here. So once we have this representation, we can define the operator L, which satisfies the Hofmann-de rank condition. And in our case, the Hofmann-de condition is that no non-trivial subalgebra can be annihilated by these derivations. That is, if for all the elements which annihilates these derivations, it has to be a part of the center of the algebra. And in our case, the algebra is generated by the CCRs. So the center is just spanned by scalars. So we would be able to then get some examples of nil-potent Lie algebras, which satisfies the Hofmann-de condition. Now, in this case, first, we saw that we have found the derivations intuitively to find the representations of the nil-potent Lie algebra. Another way that we can get this representation is first by defining the coordinates in terms of a pair of CCR and the partial derivatives. So for example, if we take the case of Heisenberg algebra, which satisfy this commutation relation, and we take some example of the classical fields. So now we can make these substitutions in these classical fields to get the fields in terms of CCRs. And hence we can take the generators to be the derivation in terms of these fields. So in this case, it will automatically satisfy the Hofmann-de condition. And so once we get these generators, we want to see that we want these generators, but if they act on the operator of multiplication by a smooth function, we want to recover the classical operator in this case, and hence we'll be able to generalize the classical theory. And once we have done that, we can prove the coercive inequalities and spectral properties for this case. The next way we can define these generators is using the quantum Dirichlet forms, which in non-commutative Dirichlet form can be defined as the integral over the scalar product of the derivations and this function eta, which satisfies some properties. And we can define this above scalar product as defined with respect to the state, which we take as the trace of e to the power minus beta, the sum of the number operators, divided by m, and the modular operator with respect to HW, which is beta, and the sum of the number operator. So here n is defined as a star a, which and we know that number operator is an operator which counts the number of particles in a quantum system. So as Yao discussed the Berling-Deny theorem earlier, it is a one-to-one correspondence between the Dirichlet forms and the symmetric Markov semigroups. And the idea of studying the classical operator semigroups comes from the desire to study the physical evolutions which are in some sense time invariant. That is, what happens in the system between time t and t plus s. It usually depends only on the time distance s. So in probability, it's called the Markov property. So we can define the quantum Markov semigroup as the semigroup of operators on von Neumann algebra or any infinite dimensional space, such that each of these operators are completely positive and it has an invariant state. So then we can define the operator Lx as the limit of ptx minus x by t, which is going to be the generator, and it uniquely determines the semigroup. Now, since the Dirichlet form is also a Markovian form, so for the generator that we considered in the non-commutative sense, we saw that the Markovian form, which is given by this expression, is of the form half and the sum of the derivations with respect to xi, and that is the xi which were just had the contribution of the second order terms and no contribution of the linear terms. So once we have this Dirichlet form, this would be equal to the scalar product f and LF. So we can get the generator LF as the integral of the sum of the adjoint of the derivations and this function eta of t. So again, the scalar product here is in terms is with respect to the state that we defined earlier, and the scalar product is defined as 1 by m and the trace of this expression. And the modular operator is defined as e to the power minus ithwf, e to the power ithw. So first, to find this quantum Dirichlet form, we need this Hamiltonian dynamics, which is the modular operator. So for this, initially we wrote the coordinates xj's in terms of these CCRs. Now we are doing the opposite thing. That is, we are writing the CCRs in terms of the different coordinates and the partial derivatives. So if we consider xj to be any general classical field in the nilpotently algebra, so it is always usually of this form. That is the derivative with respect to the xj coordinate and the sum of some constants and the fields, and this qk here is the multi-index. So in this case, we were able to find the Hamiltonian dynamics or the modular operator, and we saw that the dependence on the time will get factorized, and we get this aj, that is the CCRs, as multipliers. So now when we'll integrate it, we'll have some constants with respect to these operators. So once we have these Hamiltonian dynamics, for the general case, we can also find the general Dirichlet form and hence the operator L. But since we see that this expression, the Hamiltonian dynamics, is itself very complicated, so first we want to find it for a specific case. So if we try to find this for the Heisenberg algebra first, so we saw that we can write the classical fields x, y, and z in terms of CCRs. And by the above lemma, we can find the Hamiltonian dynamics for each of these classical fields. And we found the adjoints, which can be computed using the scalar product that we had defined. So we saw that the Dirichlet form came out to be this very long, complicated expression. And in this case here, this eta cap is just the Fourier transform of eta. So this expression for this example only has like 50 to 60 terms, which is very complicated. And we want to simplify it and make it more intuitive so that we can find some similarity with the classical case. So the further work is actually to find the quantum Dirichlet form for the general nilpotently algebras. And again, once we have this generator, we want to recover the classical operator once it acts on the operator of multiplication by a smooth function, and then prove the coercive inequalities. Again, if we take the CCR of, if here we are taking just one pair of CCR, we can define a U as the modulus of the linear combination of A and A star, where these constants can be complex numbers or bounded smooth functions of A star, or N. So this U is more general case for N. It's more general quadratic interaction. And the N is just the specific case for U. So whatever we have been proving earlier, this is just the general case. And here we see that U can be written as this expression, which is the linear combination in terms of N, A star, and A. So if we consider some fields xj and some constants lambda I, and we write the commutator of U and xj is equal to these lambda j's xj. So this is just an eigenvalue problem. And if we first let X, this classical field, to be a linear combination of one pair of CCR, which we will extend later by introducing more pair of CCRs. In this case, then we can get the eigenvalues and eigenvectors for this eigenvalue problem that we defined here. And we can write the eigenvectors, which is going to be just the simplified form of this linear combination of A and A star. And then again, what we want to do is do the similar thing that we did earlier and find the Dirichlet form and the Markov generator with respect to the state, which we have defined as the trace of e to the power minus u instead of minus n that we had defined earlier. And this state is, we can say this as, take this as the generalization of the Gaussian measure. Now, once we have these eigenvectors, we can use the theory by which was defined by Olkiewicz and Zaba, where they use the eigenvectors to prove Poincare inequalities. So we can use that and prove the Poincare inequality for this case. Now I'm going to discuss the non-commutative framework for hypercoercivity. Since we were studying the generalization of the linear diffusion generators, which will satisfy the Hofmann-La rank condition, and hypercoercivity occurs in such cases. So first, why do we need, what is hypercoercivity? So the study of the dissipative evolution equations, which involves the degenerate dissipative operator and the conservative operator. So the combination of these two implies the convergence to an equilibrium, to a uniquely determined equilibrium. But in most cases, this dissipative part is not coercive. That is, it does not admit a spectral gap, but it might have a huge kernel, which is not stable under the action of the conservative part. So in that case, it is said to be, this generator is said to be hypercoercive. So when we are given the system of evolution equations, the theory of hypercoercivity involves splitting of this operator L into symmetric and antisymmetric parts. So we can write the generator L in terms is equal to A star A plus B, where A star is always going to be symmetric and B is considered to be an antisymmetric operator, which means that B star is equal to minus B. So this hypercoercivity, the most easiest application of this is improving the dissipativity for UT in this evolution equation, where we can just use the splitting of this operator in the symmetric and antisymmetric part. So now I'll discuss Villani's theory for hypercoercivity, and then we'll see how we can extend it for the non-commutative framework. So first, it considered H to be a separable Hilbert space and V to be a finite dimensional Hilbert space. We take the operator L to be an unbounded operator from H to the tens product of H and V, which is again going to be a finite dimensional space. And B is going from H to H, which is an unbounded antisymmetric operator. Then coercivity is defined for an unbounded operator L on the Hilbert space H, which has kernel K. And we take another space, another Hilbert space H tilde, which is continuously and densely embedded in the orthogonal complement of K. And it is endowed by a scalar product and the Hermitian norm. Then it is hypercoercive, it is coercive if the real part of the scalar product of LH and H is greater than equal to this scalar lambda and the square of the norm of H. And the hypercoercivity is also defined for this operator L on the Hilbert space H tilde, which is continuously and densely embedded in the orthogonal complement of the kernel of the Hilbert space H, such that it defines this exponential decay, and this is the convergence to equilibrium. And in this definition, if C is equal to 1, it is equivalent to the definition of coercivity. So for this operator that we considered L, which is equal to A star A plus B, This part A star A is conservative, and it's a coercive operator, which implies hypercoercivity. But for B, which is going to be an antisymmetric operator, and it's non-coercive, degenerate dissipative operator. So to prove the hypercoercivity of this operator L, we would prove the coercivity of the operator L dash, which is defined as A star A plus the adjoint of the commutator of AB and the commutator of AB, instead of the hypercoercivity for L. And if this L dash is also not coercive, we can consider a further operator by extending the similar thing to obtain the hypercoercivity for this operator L. And for this operator L, we can define the iterated commutators. C0 we take as A, and Ck as the commutator of Ck minus 1b. Then for most cases, there exists like a natural number such that the intersection of the kernels of these commutators is equal to the kernel of the sum of Ck star Ck. And this equation is equivalent to the condition that the sum of this expression is coercive on the orthogonal complement of the kernel. So the main theorem, if we consider for nc equal to 1, and we take the operator L, unbounded operator, as A star A plus B, C is the commutator of AB. And if it satisfies these three conditions, we can prove that L is hypercoercive on the space H infinity by K, which is continuously and densely embedded in the orthogonal complement of K, by proving that this operator L dash, which is A star A plus C star C, is coercive in the space H infinity by K. And since this theorem is for nc equal to 1, for general case, we can define the iterated commutators to be C0 as A and CJB as Zj minus 1, Cj plus 1, and plus Rj plus 1, where these are Rjs are the remainder terms, and the Zjs are just the multipliers usually. And then we can generalize the hypothesis which was there for nc equal to 1 for this general nc. And similarly, the condition for the scalar product on this space. And again here, if the sum of the Cj star Cj is coercive, then we can prove that this generator L is hypercoercive on the space H1 by K, which is continuously and densely embedded in the orthogonal complement of the kernel. So now we discuss the non-commutative framework for hypercoercivity. So we recall that the non-commutative LP space is the completion of this von Neumann algebra, which is given by the space of operators such that the trace of the modulus of A to the power P is finite. And in this case, again, we consider the state to be the trace of e to the power minus beta n, where n is the number operator. And we take V and W to be two operators of the random arbitrary powers of A stars and A. And again, the corresponding derivations with respect to these operators, which we are taking as I, the commutator of the A and B. And we can again define the scalar product like we defined before for the non-commutative spaces by the trace of this expression. And now if we consider the scalar product of the derivations with respect to W, then we can write an expression LW, which is equal to the adjoint of delta W and delta W, where this adjoint is in terms of the scalar product, which is given here. So we see that this LW is analogous to A star A in the operator L that we considered. So now we can define the generator L as L with respect to half of W plus W star plus this term, because we saw that this is analogous to A star A because it's always going to be symmetric, and this expression is always antisymmetric. And if you ask like why we considered half of the sum of these operators, because this will ensure that these parts are also self-adjoint, because most of the studies for the partial differential equations have been done for self-adjoint operators. So once we've defined this, we want to prove the hypercoercivity for this operator L that we defined here. And the operator L, if we want to first see that how this would look like for the simple case, so we can consider V to be equal to A and W as the powers of A, then L of T would be this expression. And if we take more general case, with more general operator like W and V to be arbitrary powers of A and A stars, then it would give us more complicated expression, but it's still going to be much more simpler than how we found using the quantum Dirichlet forms. And not only this, if we can also use the representations that we saw before for nil-potent Lie algebras, and we defined the generators in that case, we can use those representations as well to write the expressions as A star A plus B, that is splitting them as the symmetric and anti-symmetric part. To prove the hypercoercivity in non-commutative spaces. Yeah, I think that's it.
Okay, thank you, Shreya. Do we have any questions? Okay, in that case, I'll ask a question. So Shreya, so I was wondering whether you could find this Dirichlet form and associated operators and a semi-group, whether you could use any of the ideas that Yao presented to find any spectral bounds, i.e. on the number of negative eigenvalues for this operator, even in the case where you have some non-symmetric part. Are there any spectral estimates you could find in this setting? Yes, for the number of eigenvalues per se?
Yes, I think we can find that. We would be able to find the spectral properties, because especially in the general quadratic interaction case.
Okay, cool.
Is that your question?
Yes, that was my question. Yes, sorry. Yes.
Okay.
Any questions? Any other questions?
Yes, I have one question, Shreya, if I may. Thank you very much for your very nice talk, first of all. And other thing is that at the beginning you present the construction for non-commutative construction for sum of squares, generalizing, yes, the expression of second order differential operator of Formander, yes, and then you get one construction of nil-potent Lie algebras. Yes?
Yeah.
My question is that because there is also a big class of Lie groups that contains nil-potent Lie algebras, let's say graded Lie groups, and this is maybe on these groups then one has partial differential operators which are hypoelliptic, like the sum of squares of Formander. You know something about this construction for that operator which has arbitrary order, like these Rockland operators, the operator that one has on graded Lie groups.
Yes, actually, we are still working for the nil-potent case, but we definitely want to do the similar thing for other graded Lie algebras, like the filiform Lie algebra as well.
Oh, okay.
Yeah.
Still, then you have considered the problem. Okay, no.
Yes.
Thank you very much.
Any other questions? Okay, well, in that case, Shreya, thank you very much for your talk. And I believe we will reconvene here at 2 p.m. Central European time with a talk of Serena Federico.
Yes. Okay.
Okay, lovely.
Thank you.
I don't know what happened, Duban. What's happening with the Zoom call? Do we come off, I assume, and then restart it at 2 o'clock, I assume? Yes.
Yes.
Thank you.